Hello and welcome to G Fun Facts Online, your home for exploring the most fascinating corners of science and technology. Today, we're venturing into a realm that sounds like it's straight out of a fantasy novel, but is actually at the bleeding edge of computer science. What if I told you the future of computing, the key to designing life-saving drugs, creating revolutionary new materials, and solving problems we can't even dream of tackling today, all comes down to a little bit of magic? Not wands and spells, but something just as mind-bending from the world of quantum physics. We're talking about quantum computers, machines with almost unimaginable power. But there's a catch, a colossal challenge that has stood in the way for decades. This power comes from a world that is incredibly, exquisitely fragile. The slightest whisper from our classical world, a tiny fluctuation in temperature or a stray magnetic field, can bring the entire complex calculation crashing down into meaningless noise. This problem, called quantum noise, has been the great antagonist in the epic story of building a quantum computer. But now, scientists have a new hero in this story, a protagonist with a mysteriously powerful name, the magic state. Today, we're going to pull back the curtain on this so-called magic. We'll find out what these states are, why they are so fundamentally crucial, and how they represent an ingenious solution that is finally helping us tame the wild frontier of quantum computing. To truly appreciate the significance of magic states, we first need to get a handle on the quantum world itself. In your phone or laptop, all information is stored in bits. These are tiny switches that can be either a 0 or a 1. Simple, reliable, on or off. But a quantum computer uses a qubit. A qubit, which can be a tiny particle like an electron or a photon, can be a 0, a 1, or, and this is the foundational concept that changes everything, it can exist in a combination of both 0 and 1 at the very same time. This is a core principle of quantum mechanics called superposition. Think of a spinning coin. While it's in the air, spinning rapidly, it's not heads and it's not tails. It's in a fuzzy, probabilistic state of both possibilities. Only when it lands on the table and you measure it does it collapse into a definite state of either heads or tails. A qubit behaves in a similar way. This ability to exist in a spectrum of states allows a quantum computer to explore a vast number of possibilities in parallel. The power grows exponentially. 2 qubits can represent 4 states at once. 3 qubits can represent 8 states. With just a few hundred qubits, you could, in theory, represent more possible states than there are atoms in the known universe. It's an explosion of computational space that classical computers can never match. Then there's another quantum phenomenon, one that Albert Einstein famously called spooky action at a distance. This is entanglement. When 2 or more qubits become entangled, their fates become intrinsically linked, no matter how far apart they are. If you measure the state of one entangled qubit, you instantly influence the state of the other, even if it's on the other side of the galaxy. This deep, spooky connection is another powerful resource for running complex quantum algorithms. But this power is a double-edged sword. The very superposition and entanglement that make qubits so mighty also make them incredibly delicate. They are highly susceptible to any unwanted disturbance from their environment, what we collectively call quantum noise. This noise causes a disastrous phenomenon called decoherence, where the qubit loses its quantumness. Its beautiful superposition collapses, its entanglement is broken, and it falls back into being a simple classical bit, either a 0 or a 1. An error in the middle of a calculation corrupts the entire thing. It's like trying to build an intricate sandcastle during a hurricane. This is the single greatest challenge in building a large, functional quantum computer, and it sets the stage for why we need a clever solution. To get a computer to do anything useful, you give it a series of fundamental instructions called gates. In a quantum computer, quantum gates are operations that manipulate the states of the qubits to run an algorithm. For a quantum computer to be truly useful, it needs what's called a universal set of gates. meaning that with this set, it can perform any possible quantum computation you can imagine. Here's where we hit a major roadblock. Quantum gates are broadly divided into two important categories: Clifford gates and non-Clifford gates. Clifford gates are the reliable workhorses. They include basic operations and are, crucially, relatively easy to implement in a way that is resistant to errors. But they have a huge limitation, proven by something called the Gotzman-Nil theorem. This theorem states that a quantum circuit made up entirely of Clifford gates can be simulated efficiently on a classical computer. In other words, a quantum computer that can only perform these easy, reliable gates offers no computational advantage over the laptop on my desk. It can't achieve that quantum advantage we're all chasing. To unlock the real power, you need to add at least one non-Clifford gate to your set. The prime example, the one everyone talks about, is the T-gate, also known as the pi/8 gate. The combination of the easy Clifford gates and this powerful T-gate is enough for universal quantum computation. So, what's the problem? Just use the T-gate, right? Well, the T-gate is the Achilles heel of the entire system. The very properties that make it powerful enough to break out of classical simulation also make it incredibly sensitive to noise and notoriously difficult to protect from errors. Directly applying a T-gate is like playing with fire. It's almost guaranteed to introduce catastrophic errors into your computation, so you're stuck in a paradox. You need the noisy, powerful gate to do anything interesting, but using it threatens to wreck your entire calculation. For years, this was the great divide stymieing progress. The ingenious solution to this conundrum is the magic state. Instead of trying to directly apply a noisy, error-prone T-gate to our precious, error-corrected data qubits, scientists devised a clever workaround. Let's use an analogy. Imagine your quantum computer is a super-sterile, dust-free cleanroom, and your data qubits are the delicate microchips you're assembling inside. The non-Clifford T-gate is like a very complex, messy, and slightly greasy tool. You absolutely do not want to bring that messy tool into your pristine cleanroom. So what do? In a separate, less clean workshop, you use the messy tool to manufacture a small, special, disposable part. You then bring this clean, prefabricated part into the sterile room and use your simple, reliable tools, the Clifford gates, to integrate it into your main assembly. You achieve the exact same result as if you had used the complex tool directly, but without contaminating your entire workspace. That special, prefabricated part is a magic state. A magic state is a specific, highly tuned quantum state that, when combined with only the easy-to-protect Clifford operations, can effectively implement a non-Clifford gate. The magic of the powerful operation is essentially encoded and stored within the state itself. The term was first coined by physicists Sergei Bravi and Alexei Kitaev in a landmark 2004 paper. They showed that with a sufficient supply of these special states, a quantum computer that can only perform easily correctable Clifford gates can achieve universal quantum computation. The process of using them is called magic state injection. Using a process akin to quantum teleportation, we can inject or transfer the effect of the magic state onto our data qubit. This allows us to perform the crucial T-gate operation without ever directly applying a noisy, physical T-gate to our logical qubits. The importance of this cannot be overstated. It's the key that unlocks the door to fault-tolerant quantum computation. It sidesteps the problem by shifting the challenge. We no longer have to worry about performing a perfect T-gate. We just have to worry about creating perfect magic states. But, as you might have guessed, there's another catch. Creating these magic states is no simple feat. They are themselves inherently fragile, and the initial preparation process is noisy, resulting in imperfect, error-ridden states. Using these flawed magic states would just introduce errors back into our computation, defeating the whole purpose. This leads us to one of the most critical processes in the entire field: magic state distillation. If our initially prepared magic states are noisy, how can we possibly use them? The answer lies in a remarkable quantum algorithm called magic state distillation. The analogy to traditional distillation is perfect. Just as a distiller takes a large volume of a weakly alcoholic solution and purifies it to produce a smaller amount of high-proof spirit, magic state distillation takes multiple noisy copies of a magic state and concentrates the magic into fewer, near-perfect ones. One of the first and most famous protocols is the 15-to-1 Bravi-Kitaev protocol. This algorithm takes 15 noisy T-type magic states as input. Through a carefully designed circuit of reliable Clifford gates and measurements, it attempts to produce a single magic state with a significantly lower error rate. Crucially, the protocol is designed to detect errors. If any are found, the resulting state is simply discarded. This post-selection process ensures that only the high-fidelity states are kept for use. The error rate of the output state scales as the cube of the input error rate, meaning each round of distillation makes the states dramatically better. Researchers are now developing many different distillation routines like 7-to-1 protocols, all trying to be more efficient. The ability to distill magic states is a cornerstone of this entire field, but this purification comes at a significant cost. Magic state distillation is a resource-intensive process. It has a high space overhead, meaning it consumes a large number of physical qubits. The 15-to-1 protocol needs at least 15 qubits just to try and make one good one. It also has a high time overhead, as the distillation circuit takes time to run. This high cost has led to the concept of magic state factories. In the blueprint for a large-scale quantum computer, a significant portion of the hardware, perhaps even the majority of it, will be dedicated to these factories, whose sole purpose is to continuously manufacture high-fidelity magic states. The main part of the computer will then consume these states as fuel. The true power of magic states is realized when they are integrated into a comprehensive quantum error correction framework, or QEC. QEC is the art of protecting quantum information from noise by encoding the information of a single logical qubit across many physical qubits. One of the most promising QEC codes is the surface code, a two-dimensional grid of qubits that is highly tolerant to errors. The surface code is great at performing Clifford gates fault-tolerantly, but it can't directly perform a T-gate. This is where everything comes together. In a surface code computer, the magic state factories produce high-fidelity T-states. These purified states are then injected into the main surface code, often using a technique with a cool name like lattice surgery, to perform the logical T-gate on the data. Recent experiments have shown this entire process is feasible, even demonstrating that the fidelity of the resulting logical magic state can be higher than what's possible with the raw physical qubits, a crucial milestone known as breaking the break-even point. So what does the future hold? The quest for more efficient distillation protocols is a top priority to reduce the immense resource cost of magic. The design of quantum computer architectures will revolve around optimizing these magic state factories. And researchers are even exploring alternatives, like magic state cultivation, using different error codes, or even entirely different types of quantum systems that might not need magic states at all. The story of magic states is a testament to the ingenuity of the quantum computing community. It's a story of turning a bug, the difficulty of noisy gates, into a feature, an elegant method for universal, fault-tolerant computation. They are the essential ingredient bridging the gap between the fragile quantum world of today and the robust, error-corrected quantum future we envision. The path is still challenging, but with each breakthrough we are getting closer to the day when the magic of quantum computation is no longer a spooky, distant dream, but a practical and transformative reality. The taming of the quantum computer is well underway, and magic states are holding the reins. Thank you for joining us on Fun Facts Online.